Hello. Now we'll start the surface tension. The first thing we have to understand is why we are defining the surface tension when we already have the pressure. The thing is, when we talk about the particles in the fluid, there are two types of particles. Not two types of particles. Particles are only of one type, but there are two types of forces they experience. So, for an example, if we look at this particle which is inside the fluid, this one, if we look at this particle, in the surrounding of this particle, there are multiple particles are of the same type. So each and every particle apply the force towards itself. So there will be particle here, particle here, particle here, particle here, and each and every particle will apply the force onto this particle. So the net force will be 0 obviously, but all these forces which are applied by the other particles, they are of the same nature. So the forces here are acting in the three-dimensional. And if we look at this particle which is at the surface, the forces experienced by this particle are similar to this, but they are only at the one half of the side. These forces are acting only on the one half of the side. So the thing is, if we see the behavior of this particle and this particle, though the particles are same, but they are experiencing the different type of force. This is in all the direction, and this particle is experiencing the force only from the one side. So that's why the forces, the way by which we used to calculate these forces we used to calculate by defining the area, and we used to calculate it by the pressure. But this method I cannot apply to solve this particle, the behavior of this particle. So for these particles, we might need something else other than the pressure if we want to calculate or if we want to understand the behavior of these particles. So that's where the surface tension comes into picture. So what we do for this particle, let's have this view. We start looking for this particle from the top. If I look for this particle from the top, there will be the surface. I'll see the surface and I'll see this particle. And this particle will experience the force parallel to the surface, these forces. So these forces can be studied by the pressure. The behavior due to these forces can be studied by the pressure because they are acting within the volume. But these forces which are acting in the plane of the surface, these forces, we might need or we will need something else, and that something else is the surface tension. Okay. So now let's discuss about these forces. These forces are parallel to the surface. So these forces are acting in the surface only. And if you see if you calculate the net of these forces onto this particle, it still is 0. So if I want to calculate these forces directly, I don't have any mean because the net force is still 0, similar to the pressure. So to calculate these forces, I might need something like the surface tension. So surface tension behaves similarly as the pressure behaves for the particle which are inside. So pressure is a measurement, pressure is a means to calculate these forces which are acting within the volume in all the direction, three-dimensional. The surface tension is a mean to calculate the forces which are acting within the plane, but the net of these forces are also 0. So that's why we define the surface tension. It's similar, it's completely similar to the pressure. Now let's define it. To define, we will need a surface. So what we do, we take a U-shaped wire. If I'm taking the U-shaped wire and onto that, I'm putting a sliding rail. There is a sliding rail. I'm putting onto the U-shaped wire. Okay. I create a surface. Now this surface, I'm creating a surface here. This is a surface, and this surface might be of soap bubble, soap solution, and this might be of the liquid also. And I'm only talking about the single surface right now. I'm not talking about how many surfaces are there. There is only single surface here. So there will be this surface. Onto everywhere there will be a surface, and there will be these forces which will be acting within this surface. Okay. So let's talk about these particles. This particle, this particle, this particle, and this particle. I'm taking 4 particles. So the particles here will experiencing the forces which are within the surface. So you see, this particle will experience the force in all the direction. This particle will also experience the force in all the direction. This also, and this also. And if I talk about the particle in between, this will experience the force from all directions. So see, if I take this particle, the net force onto this particle will be 0 because the forces are in all the direction. But if I go for these particles, the forces are in the plane but only onto the one side of the plane. So these forces, I can calculate the net force corresponding to these particles. Meaning, when I have the surface, if I'll be having a surface, then all particles within the surface will experiencing the net zero force. Net force 0, but the particle which are along the periphery, they will experience this force which will be non-zero in nature. Okay. So corresponding to these particles, I have to proceed. So one more diagram I'll make to understand this thing. And this time, I'll only talk about these particles which are at the periphery. Okay. And I'm taking only two particles, one here and one here. So you see, if I talk about this particle, net force will be onto the one side. So the resultant of this force will be perpendicular to this side. And similarly, the resultant of this force will be perpendicular to this side. So this is the surface force, which are acting in the surface. We might call it Fs. But one more thing you can see, this Fs is perpendicular to the periphery. Similarly, if I go here, this Fs, net of Fs, will be perpendicular. Here also, the net of Fs will be perpendicular to the surface. So if you remember, in case of pressure, this force used to be perpendicular to the surface. Similarly here, on the same basis, this force was perpendicular to the surface. And these forces are acting perpendicular to the periphery. Okay. And we don't take the particle in between, because if we take the particle in between, the net Fs will be 0 onto those particles. So these particles which are in contact with the periphery, they will experience the force perpendicular to the periphery. They will try to bring the periphery closer, or these forces will try to minimize the surface area. So these are surface forces which we want to study in this. They always tries to minimize the surface area. Fs, they act in such a manner so that the surface area should be minimized. And these Fs, they are always perpendicular to the periphery. They are always perpendicular to periphery, and they'll always try to minimize the surface area. This becomes the behavior. These forces are always plane. They are always acts within the surface. These Fs always acts within the surface. Within the surface. So these three properties define the Fs. They always try to minimize the surface area. They are always perpendicular to periphery, and they always acts within the surface, basically. So now this becomes the behavior of Fs, but still we don't know how to calculate these forces. To calculate these forces, I cannot proceed with these three particles, because see, this structure has 4 sides, and out of this structure, these 3 sides are fixed. So they'll not be moving ultimately. So the Fs, these 3 Fs will be balanced by the forces applied at the joint. But if I start looking at this point, this force, this is a sliding rail and which will be moving, which can move. So let's assume the length of the sliding rail is L. Okay. So the Fs is acting onto the particle. Let's think about the behavior of Fs. So Fs is acting onto the particle. More number of particle, more Fs will be there. So you see, number of particle will be proportional to the length. More will be the length, more will be the particles, and more will be the Fs. So one thing I can say about this Fs will be proportional to the length of the periphery. And obviously I'm taking the straight wire. And since I'm taking the straight wire, each and every Fs will be parallel to each other. So based upon that, I'm saying Fs is proportional to length. But if this is having a random shape, in that case, I cannot proceed here. I cannot say that Fs will be proportional to L. In that case, I might have to take the component. So just because I'm taking a straight wire to define actually, we can say Fs is proportional to L. So since Fs is proportional to L, and Fs does not depend upon anything else except the internal property. So Fs upon L will be a constant. And this constant, Fs upon L, which is a constant, this constant we define as surface tension. So that's how we define the surface tension. No doubt we don't have any mean to directly calculate the Fs, but we do have means to calculate the surface tension, because this surface tension is completely independent of the external properties, meaning it is independent of the geometry. This surface tension depends upon the internal property, meaning what kind of surface it is, what kind of material is creating the surface. So this is the internal property. So when we talk about surface tension for water is a constant, surface tension for soap solution is a constant. So once we have the surface, the material of the surface, the medium of the surface tension is defined for that. It's a constant. This is a geometrical aspect and this is the internal aspect, internal property. And by multiplying these two, you get the surface force, which will be depending upon some external and something internal. So that's how we define the surface force, with the use of surface tension. Now with the same method I can calculate the Fs here also, here also and here also. All I need to do, multiply the length with surface tension, and here also multiply the length with surface tension, and I'm assuming it has to be parallel, because if it is parallel, only in that case I can just multiply the L with T, because if it is not, in that case, if you see here, it is always perpendicular. So they have to be parallel to say here we are just adding it. Okay. So till now, in this lecture, we have seen why we are studying the surface tension, what is the need, what we cannot do with P. So the thing is, there were two particles and both of these particles were experiencing the same forces but with different way. This was experiencing the same forces in all the directions, which was making the net force 0. So for that we needed P. We defined some P, pressure, and with the help of pressure we used to calculate the perpendicular force. And here we have defined the cross-section area. So when we talk about these particles experience the force only on one side. So these forces which are acting within the volume, these forces still we can calculate with pressure. But these forces which are acting parallel, for these forces we needed a different method. And that different method we started studying here. The particles, they were experiencing the forces which were parallel to the surface. And these forces, when we studied these forces, they were acting perpendicular to the periphery. Here also, here also, here also, here also. These particles, the net force for these particles which are inside, the net for those forces were 0. So these particles we cannot proceed. We can calculate the surface force here also, but we cannot proceed. So what we did, we went for the particles which are nearby to the periphery, which are connected to the periphery. And for those particles, we come to know that these forces are acting perpendicular to the periphery everywhere. These forces were acting perpendicular to the periphery. So based upon all the study till this point we have defined, and till this point we realize the surface force is always tries to minimize the cross-section area, because the surface force was acting perpendicular and towards the solution. So the periphery, it was trying to bring the periphery closer. So when you bring the periphery closer, the surface area decreases. So the nature of Fs was to minimize the area. Similarly, this Fs was acting perpendicular to the periphery. These are the properties. It will always happen. And this Fs was acting within the surface. It was parallel. Meaning there will be no component of Fs which will be perpendicular to the surface area. So with these three particles, we cannot proceed because they are fixed. We proceeded with this particle. So as you know, the Fs was acting onto the particle. More number of particles, more number of Fs would be there. So number of particles are proportional to L. So number of the force will be proportional to L, and based upon that we said Fs upon L will be a constant, and that constant will depend upon the internal property, and that internal property of the fluid we have defined as surface tension. So surface tension was defined. It depends upon only on the internal property. Okay. Thank you.